Just make sure, can everyone hear me all right? Okay, cool. So today we're going to be talking about number theory. If you guys have been following along with like program 1, you might already have learned a little about number theory, but we'll just go over it in a little bit more depth and then discuss some other things that we use in number theory. Okay, so today we'll be talking about GCD, LCM, which I'm pretty sure you guys are aware of, and then we'll talk about remainders and the modulo system. Then we'll talk about some basic arithmetic, modular arithmetic, and then the Chinese remainder theorem. Okay, so you guys have probably all heard of the concepts of like GCD and LCM. However, you might not have learned how to calculate it properly. So GCD stands for greatest common divisor, and LCM stands for lowest common multiple, right? So first, we need to recognize something that's known as like prime factorization. So the conclusion is that every single natural number has a unique prime factorization, which means that you can write it as the multiplicative form of a group of primes. So let's say we had the numbers a and b. We can write it in terms of the primes p1, p2, p3, all the way to like pn or something, right? And here they don't necessarily have to have the exact same prime factors. It could also be to the power of like 0, right? P to the power of 0 is just going to be 1. So has everyone heard of like prime factorization? Is everyone just aware of how that sort of works? You can go into it a little bit more depth, if not, but it is an important part when you're factorizing integers and you're thinking about like modulo systems and greatest common divisor and lowest common multiple. Okay. Has everyone heard of it, or is everyone familiar with it? Kind of, yeah. So it doesn't say too much. It's basically just saying you can express what is important to note about it is that like every number has a unique prime factorization, right? And that sort of comes intuitively, or you get the same number, right? So they will have different numbers have different prime factorizations. So let's say we have two numbers a and b, and we write it out in the prime factorization form. Then the LCM, if we think about it algebraically, is basically P1. We take the maximum of E1 and F1, right? And we take that power as the first power of P1. And then we do the same for all the primes that we have within A and B. And as a result, we can express it algebraically like this. And you can consider like LCM as it's the smallest number that both divides, like A can divide into and B can divide into, right? So it's the smallest number that A and B can fit into. So you can't have a power smaller than the maximum of either of these, or else you won't be able to fit it in. You won't be able to fit, say, if E1 was, if E1 was greater than F1, that basically means you need something that's bigger than E1, so you can fit E1 inside, right? So that's sort of the idea for LCM, and then it's exactly sort of the opposite for GCD. So GCD is basically the biggest group you can fit both of A and B into, right? You can divide, GCD is the biggest number that divides into both A and B. So you want to if you have a bigger number than the minimum of, forget this again, if we have something smaller than f1 as a GCD, we can always find something bigger that also divides, that you can divide it into, right? So that's sort of the idea behind GCD and LCM. So when you calculate it, it's really useful to actually factorize it into primes, especially if the numbers are really big. It can be really useful if you find all the primes of the numbers you're looking at, and then just pick either the biggest or the smallest for LCM and then GCD. Does everyone sort of understand that idea? Yeah, okay then. Then let's look at another really useful conclusion that might either make like calculating one of LCM or GCD much easier if you know the other one. So we know the statement states that if you times the GCD of the numbers A and B together and the LCM of A and B together, it should just equal A and B. And if we think about how to prove this, we can just use these two, right? So would get LCM AB GCD AB equals, what does it equal? If we want to times all of them together and then pair everything up. So the ideas as to like what the power of P1 would have to be in this case. Yeah, so it's just the maximum plus minimum of E1 and F1, right? And that really should just equal E1 plus F1, because one of them has to be the maximum, then the other one has to be the minimum, right? Because there's only two numbers. We're only thinking about E1 and F1. There's no other numbers we need to consider. So it's either like this or it's like this. So it's one or the other, and whichever one of these, max plus min is always just going to be E1 plus F1. And we do that for the same. We do the exact same for all of them. So it really should just be 2 plus F2 plus 3. Right. And it's not a really vigorous proof, but you kind of get the idea that we see that all of them has to be E1 plus F1, right? Or E2 plus F2. And this is just the equivalent to A times B. So we can conclude that. Like this, right? So that's sort of the idea. Okay, then let's think about these two exercises. Let's do the first one. I'll give all of you guys like 2 minutes to do the first one, and then we can discuss it together. It's really just a calculation problem. I don't even know what the answer is, but like if you go through our process of discuss like factorize into primes and then choose each of them respectively, then you should get the answer anyway. So let's think about that for a bit. Okay, did everyone get okay. So did everyone get the same prime factorizations for these two numbers? Yes? Let me know, because I just did this like myself, so I don't actually know either. Okay, sure. Okay, so we have the same prime factorization of these. So let's say what primes we have in each of these numbers, right? So they each have 3, each have 2, but 54 to the power of 7, right? So we can actually write this as 7 to the power of 0, because we know that an integer to the power of 0 is just 1, right? So we can write it like this to make our lives a bit easier. Okay, and then we remember, what does LCM mean? Well, LCM, we want to take the maximum of each power, right? So GCD would be the minimum, but for LCM, we want to take the maximum because we want to fit everything inside, right? So it needs to be sufficiently big enough. Then we can say LCM of 4 and equals. Let's consider the 3 first. So there's 3 primes you need to consider, because these are the only primes that appear in our 2 numbers, right? So 3 appears here, appears 3 times, here appears 2 times. We pick the maximum of that, so that's 3. Then let's consider 7, 0, and 1, so 7 to the power of 1. So that's 1 is obviously bigger than 0, and then 2 to the power of 2 and 2 to the power of 1, so we do this. And that should be our answer. Yep, and I see like a lot of people have gotten the right answer, which is really, really good. I'm not gonna expand it out because I'm sure like it just works if you do, but that's just calculation. Anyways, so on to exercise 2. This is a little bit different to how you might consider like LCM and GCD, but what if a question asked us to compare the size of these 4 like values, right? How do we know which one's bigger, which one's smaller? Well, we can have a look at the definition of these, right? And we should be able to make a conclusion about the respective size of these 4 values. So this basically is like, say we have 2 numbers, A1, A2, and we're given that A1 is greater or equal to A2, right? So it's asking us to compare A1 and A2. Okay, I'll give you guys all like 2 minutes again to have to think about it. And what's really important here is to consider the idea of like, you can consider very algebraically in terms of like the definition of LCM and GCD, or you can think of more like intuitively, right? So LCM has to be sort of big enough so things can fit into it. Both these numbers can fit into it and divide into it, whereas GCD has to be like small enough so that it can divide into both the numbers we're thinking about, right? So there's 2 ways you can do it. Yes, both work, but if you wanted to really explain it quite clearly, you'd have to think about it algebraically, I guess. Yeah. Okay. And here it's like we're thinking about A1 and A2 separately, right? So you can also, if you really want, you can consider this as well. Like maybe this is even to add a little bit to the problem, but it should be the same sort of idea. Yeah, okay, so I've seen some good ideas, and I think everyone gets the sort of like the thinking behind it. So we already know A1 greater equals to A2, right? So we have that. And then we know that lowest common multiple, A1 has to divide. Okay, this is like divide sign. I'm not sure if everyone's aware, like know of it that much, but it's alright. Like it basically means, this just means that A1 divides into the LCM of A1 and A2, right? And we can use this conclusion to say that, well, quite intuitively, any number that divides into another number has to be smaller or equal to it, right? And we know that A2 so like we said, so we can do something like this, right? Does everybody kind of get the idea behind it? Does everyone understand it? If you have any questions, just feel free to ask as well, and we can go over in a little more detail. Or if you don't understand like notation or anything. So this, like I said before, this notation just means it is able to divide into it. So the left-hand side is able to divide into the right-hand side. And same for this, right? So it should have, if there aren't any questions, is everyone happy to going on to the next part? Let's go. Oh. Okay, then. Now let's consider remainders of modulo. So modulo is actually very similar to remainders. If you're just thinking about it, then it's basically the same as if we're just considering the remainder of a number when dividing by another number, right? So if we consider a number x equals a n plus r, where r is the remainder, so we should be able to say this, right? Because remainders, if it gets any bigger than this, well then it would just mean that a is a little bit bigger, right? Because a is the quotient and we're dividing by a. And we're writing our x in terms of n. So we have this, and then we can say, if we want to change this into a mod format, we just say x is congruent. So three horizontal lines is basically known as the congruent sign in mod. So it's a little bit different to just like the normal ones we have for 2. We have to use the congruent sign, so make sure to remember 3 horizontal bars. Okay, so we can say x is congruent to r mod n. So it should just make sense if we're considering it as the remainder. So we're dividing by this and we get a remainder of this. That's just the way you can think about it. And this would also mean that x minus r is divisible by n, right? Because we know x equals n plus r. And then if we minus it off, well, it's quite obviously divisible by n because a is an integer. Right, and then, let's just say this is an integer, and it's divisible by n. Okay, so now, does everyone understand the system of modulo and how to write it? It's very, very similar to remainders. You can just think about it as remainders. For now, but does everyone understand what we're talking about here? Okay. Awesome. Okay, then what about if we wanted to express this below under modulo 24? I'll give everyone like 1 minute to do this, and if anyone wants to share what they think, then that's like be also really cool if you just shared how you did it. Yep. Does anyone want to share? Like, if you wanted to share, maybe just share what you considered as a quotient, which part you consider as the remainder, and then how you just, it's really quick and easy. If not, it's also fine. So just a reminder that 3 lines is congruent. So you can refer to it as being congruent. Okay, I've seen some good responses. If nobody really wants to share, I mean, it's quite simple, so we can go over it really quick. Basically, we're divided by 24, right? So we're considering n as quotient. And then it just leaves the remainder of 13, so we'll just write x 24. Right, and that's quite easy. But what if we wanted to express, because 13 is bigger than a half of 24, which is 12, right? So what if we wanted to express it as a negative? So what you can do under modular systems, which you don't really do in like remainder, is we can write things as negative. Like we can write the remainder as a negative instead of positive, right? So how we would do that is basically think of 24 as congruent to 0 mod like 24, right? And that's pretty obvious, I guess, because if you divide 24 by 24, you get a remainder of 0, right? So that makes a bit more sense. And like we'll be saying below, so our next part is going to be modular arithmetic. What you can do is you can easily subtract like 11 from both sides, and that should still be true. Right, so what we can get is, so if we really wanted to, we could write x congruent to negative 11, 24. Something like this. And that should also be true because 13 is congruent to negative 11. Yeah, so that's also how you can change something into negative form if you wanted to. But you don't necessarily always want to. It doesn't make much of a difference. So now let's talk about modular arithmetic. So arithmetic processes include, like, what arithmetic processes can we think of? Like just a really basic one we use in everyday, like algebra. Can anyone think of any? Yes, no. No, okay. Well, the arithmetic processes are like everyday things that we use. So it's addition, subtraction, multiplication, and division, right? That's basically our arithmetic processes. So under the modular system, it's very, very similar to normal equivalent systems that you might be aware of for arithmetic processes, except for division. So addition works the same way as if you were just like congruent is basically going to be the same as if you have equals sign. So you can add on both sides and you can subtract on both sides like you would with just normal equal signs, and you can actually times both sides as well. So say we had a mod, and we can easily do anything like let's say we subtract m from both sides. This is still true, so we can subtract and it's still true. We can add, it's both true. We can time, it's still going to be both true as long as we do the same to both sides, right? But it's a little bit different for division because it's not always going to be the same, and we'll talk about that a little bit later. But let's consider the problem we have below, right? Okay, I'll give everyone, again, 2 minutes to have a think about it. How could we like use arithmetic processes like we would in just normal algebra to find what 10x is congruent to in mod 23? So just think about, you don't actually even, okay, you do need subtraction and multiplication and addition, but you don't need division or anything. So can all have a think about it. And if anyone has any ideas or if I see any good answers, I might call on you just to share your thoughts. But no pressure, right? Okay, I've seen some good answers. I'm just gonna pick on Jackie. Do you want to share how you did it? Yeah.
Okay. Sorry. Well, I first added like 3x to both sides, so got 5x. Then the 3 line is congruent to 34 mod 23.
Yep.
And then that could be put into 5x is congruent to 11 mod 23.
So yeah, we subtract 13 from 11 from both, or what do we? My bad. 13 from both sides.
Subtract 13 from both sides, yeah, until 5x is congruent to 34 mod 23.
Yep.
And then I've changed that into 5x is congruent to 11 mod 23.
Okay, so we have 5x. Yeah, and because the question asks for 10x, so what we can do here is we notice that 5x times 2 is like 10x, right? So we times 2 on both sides. And that's 68 mod 23. And we could leave it at 68, right? But we really do want to simplify it a little bit, right? Because remember we talked about when we're thinking about a residue class, which is the possible like remainders we can get, it really should lie between, like in this case, 22 and 0, right? Because if it gets any bigger than 22, like 23 or 24, we can subtract 23 again from it and we can simplify it, right? So we really should get a number that lies between 0 and 22. And what we can do is we just find that 68 equals 23 times 2 plus 22, I believe. So what we can do is, and remember 23 mod 23 is 0 because it divides into 23. So we should just get something like this, right? And I saw a lot of people that did get this answer, which was really good. And Isabel had a really interesting answer as well because she actually changed it to a negative, which is which is like a good move, right? Because 22 is a big number, especially compared to 23, right? So what we can do to further simplify it a little bit is we know that 22 is congruent to -1 mod 23, right? And we can just really write it like this. And that's basically how you can figure out this question. And that's really good. Cool. So just remember, like, don't be intimidated by the congruence sign. For basic processes, it's all the same, except like when you're faced with division, just be a little bit more careful, like we'll talk about later. But the same general rules apply. So now let's think about division rules in modular system. So let's consider, okay, this isn't even ignore my example. Okay. Let's say we have like okay, let's say we have this. And this is true, right? Because 6 mod 3 is 0 and 9 mod 3 is also 0, right? So it makes sense that we have this relationship. So this is a true statement. But if we had something like this in like normal equivalence, like with the equal sign, we might think, oh, well, they have a common divisor like 3, right? So how about we simplify it by dividing both sides by 3? And if we do try to do something like this, we get 3 congruent to 2 mod 3. And this isn't true, right? Because like 3 mod 3 is 0, but 2 mod 3 is still 2. So this is an incorrect statement. So obviously when we've divided something, something's gone wrong. Something has we've broken something. And that's generally what like the division rule is talking about. So ignore the example because it's not true at all. But okay. So more specifically, say we're given a question where we have an unknown variable, right? That's generally when we want to divide because we want to get something like x by itself. We want to find what x is congruent to mod n. That's generally why we would think of dividing in the modular system. So let's say we're given ax is congruent to b mod n. And we also know that the greatest common divisor of a and b is equal to m, and the greatest common divisor of m and n is 1, which means that they're co-prime, right? So co-prime is, or relatively prime, refers to when the GCD between the two numbers is 1. So they don't have any common divisors except 1. So the rule is basically telling us that when we have these conditions, we can divide. And only when we have these conditions, we can divide in modulo n and remain in modulo n, right? So what we can do here is if we do have these conditions, we do something like this. And this is still a true statement, right? Because what is most important about this is that m, the divisor between a and b, has to be co-prime with n. Because if it's also shared with n, like you can't promise that the relationship still holds, that you're not dividing away like an important part of the modulo like equivalence that we need to keep it true. So we don't want something like we had here happening. So we want to make sure that we only divide when it doesn't even have to be the greatest common divisor. It can just be a divisor of a and b. So it has to both divide into a and b, but it has to be co-prime with n. And here we can still promise that both these numbers here and here are still integers, right? Because m divides into a and m divides into b. And we should get something like this. That can help simplify our problem. But what if m isn't co-prime to n, right? We still want to simplify it. But what other ways can we do it if m isn't co-prime? So what this basically means is it's not equal to 1. Well, then we can't stay under the mod n system. We have to change it as well. So if we do want to divide, then we have to divide like this. Right? And this is actually, this just means that the common divisor of a, b, and n is equal to m. It doesn't necessarily have to be the greatest common divisor. It just means that m has to divide into a, m has to divide into b, and m has to divide into n. Right? And that's an important condition. And this is still true. But what's important here is that we're no longer in mod n, we're in mod n divided by m. So that's quite important. Let's try a problem. So let's say we have 6x congruent to 4 mod. How could we simplify something like this? Right, so we obviously notice something like, oh, well, these are all even numbers. Maybe you can simplify it. Oh, and we want to find like what x is common, right? Maybe no. Let's say we just want to find something like this. Okay. Oh, let's just say we want to simplify it, right? Simplify it as far as we can. Well, then they're all even. Let's say we just divide everything by 2. Right. And we get something like this. Can we simplify it further? Does anyone have any ideas we could simplify it further and make our lives a bit easier? Especially if we can express it as just x. So what is x congruent to? Any ideas? How I'd think about it is to consider the coefficient. Right, because you can also change the coefficient. Like you can manipulate it a bit to make it so it's easier for you to figure out the solution. Does anyone have any ideas? I'll give everyone like 2 minutes to think about it, because this is something quite interesting you can do here. Okay, awesome. So, okay. There are actually quite a few ways you can think about it. Like, if you don't know how things should really be, if you don't know what the answer should be, well, we know x, we're just trying to find the value or values of x, right? So how about we just substitute some random numbers? Say we substitute 1. So is 3 congruent to 2 mod 4? Well, obviously not, right? Because we know that 3 is just leaves a remainder of 3 and 2 just leaves a remainder of 2, and they just aren't equivalent. What about if we did x equals to 2? Would get something like 6, right? And is 6 congruent to 2 mod 4? Yes, right? Because 6 leaves a remainder of 2 when you divide by 4. So this is true. So we know that, well, whatever we get for x, it should include the value x equals 2, right? And we can continue this process for a little bit longer. And what we'll notice is like, we start to get things repeating, right? We start to get things repeating when we have the same mod 4. If we have x in the same mod 4, let's go a little bit further. Let's consider x is equal to 3. Right? And 9 is congruent to, let's say we divide by 4 and then we think about the remainder, right? We get 1. Right, and 1 is obviously not congruent to 2. So x equals 3 shouldn't work. Let's quickly consider 4. Well, it should just equal 0, right? Because you're timesing by 4. So this shouldn't work either. And we notice that, well, only x equals 2 works in this case, right? And we can keep going with 5 and then with 6. And we'll notice 5 doesn't work either. But then 6 works again. And then 10 should work again. The next time it works should be 10. And the only relation, well, not the only relationship, the relationship we can see between all these numbers is that we should be looking for something like this, right? X leaves a remainder of 2 when it's divided by 4, because 6 divided by 4 leaves a remainder of 2, and then 10 divided by 4 leaves a remainder of 2 as well. And that should just be our system of solutions. But what if we wanted to prove that like a bit more in detail and more convincing, right? We can't just trial and error every single number, right? Okay. What we can do here is let's think about what 3 is in mod 4, right? 3 is equal to 3 mod 4, quite obviously, but it's also equal to -1 mod 4, right? So what if we substituted 3 for -1? It should be, it's equivalent in under mod 4, so we can do that quite easily. So what we can do is instead of 3x, we write it as -1 times x, and that's -x mod 4. Right, and then we'd get mod 4. See, and then what we can do here now, if we have negative, it's the same as under normal equal sign. We times like by -1 and then times by -1 here. We just get x equals -2 mod 4. But -2 mod 4 is equal to 2, right? Mod 4. Right, so we just basically get something like this. Does that make sense to everyone? Okay. So the really important part of this is, I'd say, here, when we have to notice that 3 is congruent to -1 mod 4, right? And then that's the key idea for simplifying it down a bit further. Yeah. What about another way of thinking about it? So yes, we can change 3 from -1, but what if we thought about it as multiplication? Because we know multiplication always works, right? We can't necessarily divide by 3 right here, but we can times, right? We can times 3x by whatever we'd like, as long as we times the other side as well. So we have this. Then let's times both sides by 3. Like, then we'd get 9x congruent to 6 mod 4. And 6, like we've talked about, is congruent to 2, right? So we can write it like this. And 9 write this. Right, so there are 2 ways of thinking about it. And this one is just more of a multiplication format, while this is mainly just noticing that 3 is congruent to -1. And the first way we did it, it's really good because in this case, we notice that 3 is congruent to -1 mod 4, right? But it's not always going to be the case. So if it's not the case, like, we might not be able to easily just change it to -x. Whereas the second way we do it, as long as like the coefficient, or in this case 3, is co-prime with the modulo system under, you can always basically do it. You can find like a number where you can times both sides by a number where it results in just 1. Right? This is the coefficient of 1. And in the handout, there is an extra like session for experts, I guess, that considers inverses, right? And this uses the idea that some numbers have an inverse under modulo system, right? And we can use that to find what x has to be congruent to. So if you're interested in something like that, definitely check out inverses. It's very useful in both in modulo division, as it makes it a lot easier, or it just gives you another way of interpreting what division is in the modulo system. So now, does everyone have a good idea about how these arithmetic processes work in modulo? Yeah, okay, any questions? Feel free to shout out if you do have any questions at all. Especially since today I think we have a bit more time, we don't have as much content to cover, so if you want to go over anything in a bit more detail, I think that could also be really good.
Sorry, on the pile of line you write on the right hand side, how does it change from the step 9 is congruent to 1 mod 4? How did you got that?
Oh, okay. So we have something like, do you mean this step?
Yep.
So let's think about how can we write 9 in terms of 4, right? Well, 9 is equal to 2 times 4 plus 1, right? So this means that if we divide 9 by 4, it leaves a remainder of, it's 2 remainder 1, right? We really just care about the remainder part of this. So we know that it leaves a remainder of 1. So 9 should be congruent to 1 mod 4. That makes sense, like,
Yes.
just in terms of how we're expressing. Pardon?
Yes, that makes sense. Thank you.
Yep. Another way of thinking about it is like, how do you know that the equivalents exist? Well, what if I just say we have a congruent to mod n? Well, this value is going to be always true if we subtract b from both sides, right? Something like this. Well, this has to mean that a minus b n divides into a minus b, right? So as long as we can subtract one side from the other side and the result we get is something that's divisible by n, or like the modulo system we're under, then it should be true. The equivalence should be true, right? And in this case, 9 minus 1 is 8. 8 is divisible by 4, so it should be true as well. Okay. Then let's move on to the part of the Chinese remainder theorem. And this is a bit more confusing and it's definitely more difficult. But what it states is the Chinese remainder theorem basically tells us that there's a unique solution to like simultaneous linear congruences in coprime moduli. And that's like a bit of a mouthful and it's a bit confusing. But what we can think about it is if in a question we're given a lot of conditions, like we sometimes are given a lot of simultaneous equations, right? And they tell us to find the value of x or find something like that. That's kind of the same idea as what we're considering here, but it has to be under like a modulo system. Say we're given x is congruent to something mod. And we're given a lot of conditions. It doesn't matter how many we're really given, but we're given these, right? And A1, A2, all the way to AN, there's no specific relationship between them. It's just the condition we're given, right? And the only really important condition we have to consider is that M1, M2, Mn must be pairwise coprime. Does anyone know what the meaning of pairwise coprime means? So remember that coprime means that the GCD of like any two numbers is equal to 1. So what would like something like pairwise coprime for a large group of numbers have to mean? Any ideas? Feel free to just share any ideas in the right. Or you can send it to me or just send it to everyone. Like I said, like it's really beneficial if you do send it to everyone and we can discuss it like together. Okay. So yeah, it might sound like, oh, does it mean that all these numbers together have a number, like their greatest common divisor is 1? But it's not quite that. It just basically means is, okay, so I've seen a really good response. Yep. So it's if you pick 2 from this group of numbers, right? So we have a group of numbers M1, M2, M3, M4, all the way until M, right? This set of numbers. Well, pairwise coprime means that we pick any 2 numbers from this set randomly. It doesn't matter which ones we pick. Say we picked like M6 and N-4. Like I picked them completely randomly, but the condition for pairwise coprime means that any 2 randomly picked, their greatest common divisor is also equal to 1. You can also think about this as for all of them. So for all of the numbers in our set, any 2 of them have a greatest common divisor of 1. So let's think about a set of numbers 2, 3. Is this set of numbers pairwise coprime? Okay, no, right? So why isn't it pairwise coprime? Does anyone want to share like in the dirt? And yeah. Would you like to share that with everyone in the public chat? Let's say, so I've seen good responses from everyone. I'm just gonna pick on someone randomly, okay? Tony, do you want to share how you thought about it and why you said like no, it's not pairwise coprime? Yeah, right. Okay, so fair enough. Good job. Okay, so what if we randomly pick 2 and 4, right? The other ones seem to work, right? Because if we pick 2 and 3, 3 and 5, well, they seem to work, so they should all be fine. But what if we just randomly pick 2 and 4? Well, their greatest common divisor is 2, right? And then that just means they're not pairwise coprime. So that's basically what pairwise coprime means. It means that in our set of numbers, if we pick any random 2, it should always have the greatest common divisor of 1. And this is the condition we need for the Chinese remainder theorem. So we need to know that the set of not necessarily the residue class we get, but this part. So the part we're considering for the modulo, they have to be pairwise coprime. So that's our condition. So M1, M2, all the way to Mn, they don't share any common factors. Okay, and after we have this, after we understand that part, what does the Chinese remainder system theorem actually tell us? Well, it tells us that there is a solution for x. So there's always going to be a solution for x, and this solution for x is unique under modulo and this just means that if we're considering x under modulo m1 times m2 all the way until times mn, there's only one residue class, or you can think about as one remainder that satisfies x. So it doesn't mean that there's only one x that exists. It means that all these x's have to have one unique remainder when we're under modulo m1 times m2 all the way to mn. Does that make sense to everyone? So first, it tells us there does exist a solution, because not necessarily all the time we're going to get a solution for our set of equations, right? Say if we had like x equals 2 and then x equals 6. If we had something like this, we're never going to get a solution, right? Because they're contradictory statements. But what the Chinese remainder theorem tells us is as long as it satisfies the conditions we have here, there's always going to be a solution, and then the solution is always going to have unique remainder under modulo like m1, m2, m3, all the way to mn. Does that make sense to everyone? Yes. So yes, pairwise coprime would mean that all the numbers are coprime to each other, like collectively together. Obviously, their greatest common divisor is going to be equal to 1. But if we considered them like 2, any random 2 of them together as well, it's also going to be equal to 1. So being pairwise coprime is stronger than just being coprime, right? Because like the example we had before, 2, 3, 4, 5, 7. If we considered the greatest common divisor of all these numbers, well, that's still going to be equal to 1, right? But we can't say that's pairwise coprime because 2 and 4 exist together. So yes, it's if all the numbers are just coprime to each other, but in pairs. We have to consider in pairs. So we can't consider it collectively together. We need to consider it in pairs. Okay. Okay. So everyone understands what the Chinese remainder theorem is talking about? Or we can definitely go into it a bit more detail if you would like. Okay, let's try a question really quick. So say we have with the problem here, right? X. We have this. So 2x corresponding to 5 mod 7, 3x corresponding to 4 mod 8. Because we're a little bit short on time, we'll just run through this together, right? Okay, so how can we consider this? Well, there's 2 ways we could do it. We can just go straight into it and then consider it as 2x and 3x, which I personally don't prefer. What we can do is simplify it, right? Because 2 and 3, so we want to find x, essentially. That's the main goal of this problem, but we don't want the coefficients 2 or 3. So how about we simplify the first equation? What we can do is, well, what if we times both sides by 4? We times it by 4, like our motivation for timesing by 4 is that if I times a coefficient by 4, we get 8, right? And 8 is congruent to 1 mod 7. And that's what we want, right? We want x to have a coefficient of 1. Right, so that's our motivation. And after we times both sides by 4, we get something like this. And then if we simplify, like we substitute this part in, we get something like this. And this is equal to 6, right? Okay. I'll go a little bit faster, but we can talk about it afterwards, right? So we get something like this. And this is a lot better than what we had before. So let's say this is. And then let's consider our second power. How can we simplify this now? So like use the same process we did before. We want to make the coefficient into 1, right? But right now we have 3. So what number is really good that we can like times our equation by to get 1. Any ideas? Yeah. Okay, really good job. Okay, isn't it 8? No, not necessarily, because okay, so 8 is congruent to 1 mod 7, right? Because if we think about it, 8 minus 1 is congruent to 0 mod 7. And that's pretty obvious because 7 is congruent to 0 mod 7. Well, let's add 1 to both sides, right? So say add 1 to both sides. Well, then this statement should also be true. And then we'd get something like this. We get congruent to 1 mod 7. So that's how you can think about it. So start with a multiple of 7. Well, that's obviously going to be congruent to 0, right? And then add however much we need to it, and then we should still have the equivalence. Anyways, I saw a really good idea to times both sides by 3. And what do we get there? We get 9x, right? And that's congruent to 12, 9, 8. And what's really good about 9 is that 9 is congruent to 1 wide. Okay. And if you wanted to think about this a little more detail, we know that this is true, then this should also be true, right? Because we know that addition works, then we should have this, right? So this is just a little addition process. Okay, and then we can substitute 1 instead of 9. So we get 1 x congruent to 12 mod 8. And let's simplify a little bit further. We get something like this. So now we have 2 equations of x is congruent to 6 mod 7 and x is congruent to 4 mod 8. And this looks a lot nicer because we have it just in terms of x, right? So now what we can do is, let's change, if we wanted to think about it like as we might do in everyday, like just with remainders and stuff, let's change x back into like 7n plus 6, right? Because before we were changing from this format into the modulo format, but we can do the exact same, right? And that should also work, right? We just know that n is going to be like an integer. We don't necessarily know which integer it is, but we know it is an integer, and that's enough. So let's substitute. Does everyone understand this step of how we change from 6 mod 7 into 7n plus 6? Yes? Okay, cool. So, well, we can change it to that format, and let's substitute. Okay, so now this process is basically dealing with the first equation we have. Now we have to deal with the second. So what we can do is we can write this as right, and then what we can get is this, right? And then what we can do is Okay. How should we go on from here? Oh, okay. What are some ideas onto how we could go from here to somewhere else? So we want to get, so the main goal now is to get n alone, right? So we want to get it as something in terms of n. So we want to find n. Yep, so definitely we'd have the condition that 7n plus 2 is a multiple of 8. But what if we wanted to consider n alone? Like we did before, what number could we times by, or like not even times by, to get it as n alone? So n with a coefficient of 1, what's a good number we could multiply by? Okay, so yes. So Isabel has a really good idea of timesing by 7. So let's do that. And we times by 7 because we know that 7 times 7 is equal to like 49 mod 8. And 49 is congruent to 1 mod 8. Right, and we know this sort of by, this is true because 8 times 6 is 48. So then 49 should be equal to 1 mod 8 if we add 1 to both sides, right? So we can consider it like something like that. So we know that 7 times 7 is we use -2 here, but if you wanted to, you can consider that as 6 if you're more familiar with like positive notation, but either or works. Okay, and we get something like this. Okay, let's simplify that a little bit further. I would actually suggest if you're starting off to use 6 instead of -2 because it might confuse you a bit as to like, oh, how do I change from negative to positive, positive to negative? So if we did just use 6, then we'd just get 42, right? And we get something like this, right? So change 49 for 1, and we get something like this. Right, okay, does this make sense to everyone? You don't have to necessarily know what we're gonna do next step, but just think about it as in itself. Does everyone understand how we kind of changed from here, this statement, onto this statement? So we used a water process to get n alone. Yes. Okay. If you don't, just shout out and we can go over it really quickly. But that makes sense. We'll keep going. Okay. Well, now we know something about n, right? Before we didn't know anything about n. We only knew that n existed and it was an integer, right? So here we had the only assumption we could make was that n is an integer. Right now, we know another condition about it, right? And that's good because that's giving us more information about x itself. So we can use this information to actually find like x more specifically. So let's use another constant. It doesn't really matter, but okay, let's write it like this. So we can do something like this, right? Again, we won't know anything about r, we just know that r is an integer. So we can write it like something like this. Well, we know that x equals 7 and plus, what was it, 6? Let's substitute n equals into this. So what would that be? What would x be in terms of stuff like this? if we substituted the n out for 8r plus 2? What would we get? Yeah, really good. So, just think about it as we usually would, right? So what we would do is something like this, right? So instead of n, we write 8r plus 2, and we'd get 56. We times it out, right? And we get 56r plus 20. Right? And this is good, right? By the Chinese remainder theorem, like if I just write it as this, we know that x should have unique solution under mod. See, remember, like we talked about way back, it should have a unique solution under M1, M2, M3, all the way to MK, right? But in this case, in our problem right here, we're only considering it with M1 equals 7 and M2 equals 8. So it should have a unique solution under 7 times 8, right? And that should be mod 56. And right now, we notice something about this. What would x be if we wrote it as mod 56? Yeah, right. It would be equal to 20. Like we talked about before, how to express the numbers in terms of in mod. Well, this should be true, right? And because it's a unique modular relationship, like one solution for the residue class, so this means that we can't get like 21. X can't be congruent to 21, it can't be congruent to 22, it can't be congruent to 2, or like whatever. It can only be congruent to 20 mod 56, right? And we have basically found the solution for this. So say we wanted just to be really, really sure that our solution is correct. Then what we can do is we can substitute back into our initial equation. So that was 2x congruent to 5. And to 4. Okay, what would we get for that? So let's say we just substituted. So all we know is that x is congruent to 20 mod 56, but so this means that x could possibly be equal to 20, right? So 20 should theoretically satisfy our conditions. So let's look if that is true. Is this true? Well, 40 is equal to 5, is congruent to 5 mod 7. Well, we can test this. We know that 35 is congruent to 0 mod 7. So if we add 5 to both sides, well then 40 should be congruent to 5 mod 7. So this is correct. Well then let's test the second one, just to be sure. So we want something like this, right? So, well, we know that 56 is congruent to 0 mod 8. Right, because 56 divides into 8, and then let's add 4 to both sides, and we should get something like this. And both of these match up, so this matches up with that. So we're pretty certain that our solution, well, at least our congruent solution, is correct, right? Because at least the smallest one we can think of, like x equals 20, satisfies it. But it's not a unique, like it's not one solution. So it's also 20, it can be equal to 20, like we tested before. It could be equal to 20 plus 56, it can be equal to 20 plus 56 times 2, or 20 plus 56 times It's the variable like y, and y can just be any integer at all. And so there's like an infinite number of actual solutions, but the commonality between all of them is that they give 20 when they're divided by 56. I can definitely send out the notes after class, but just in terms of what we talked about, does everyone sort of understand how we've gone from what we had before into this? So this is just testing our solution. It's not compulsory, but it could be really good if you're dealing with like a lot of numbers and a lot of equations, and we test our solution. It can make our lives like a lot easier just to make sure we haven't made a mistake when we've been like going through all of this process. Okay, does everyone understand? Feel free to like bring up any questions you might have. And a lot of the time when we're thinking about like Chinese remainder theorem, it's not even asking us to prove, like to find all the solutions or to find the unique solution for x. Sometimes it's actually just gonna be asking that there does exist a solution. Well, we can sometimes say like by the Chinese remainder theorem, we know that there is a solution for x. And sometimes that's enough to prove a question, but it really depends on what it's asking you. But it can be really handy if you're thinking about stuff like this. Especially the unique solution part is quite useful. Any questions? No? Okay. Well, we did go a little bit over time, so my apologies for that. And as usual, if you do come up with any problems or like questions after this class, just email myself or our like main account and someone will get back to you. If you do attempt any problems, feel free to send them out. And yes, I know some of you have sent problems to me. I will get back to you guys about it.